Hello, this is an introduction to mTree and experimental economics as it will be used in mTree. So, before we get too deep into mTree itself as a platform for programming economics experiments, we'll want to define some terms that you'll see with some frequency in the mTree system that are based on earlier ideas discussed in experimental economics. So in this particular screencast, we'll discuss what mTree is more towards the end. We'll discuss the basic components of a microeconomic system. Mostly we'll be drawing from Vernon Smith's work, and we'll look in particular at the role of environments, institutions, and agents to give you an idea of what we'll use them in mTree for. We'll also look at how these types of systems can be constructed. So the idea here is we'll show you the importance of passing messages both in the Vernon Smith coverage of the topic as well as set it up so that you understand message passing when you start programming mTree experiments. And then we'll start to look at how these things can be implemented programmatically. In particular, we'll reference the actor model with the idea here of not providing necessarily too much depth on the actor model, but just a sufficient introduction so that you understand where you will be programming as we go through that in later screencasts. So we'll tie and conclude this screencast with a discussion of the features of mTree and what we think makes it useful as an experimental economics framework. Okay, so in order to set this up, we first want to talk about economies. So in this instance, we're suggesting perhaps you can consider a miniature economy. And so normally you might think of people buying things or trying to buy things in a small economy. And so one of the things you can consider is that these types of transactions will typically involve multiple agents or persons, and they'll be normally divided in their roles. So you'll have some buyers and some sellers. Additionally, there'll be some rules about how the transactions can actually take place. So, what type of currency is allowed? Do you have to have escrow? Stuff like that. And then finally, there'll be assets which the agents have control over, including money to purchase the goods. The goods themselves, of course, are also an asset, and so on and so forth. So, once we start to agree on what a miniature economy contains, we might want to experiment by changing how the transactions might occur. So you can imagine that with a idealized picture of an economy, you can then start changing again some of these transaction rules and seeing does this affect the way in which transactions occur inside of this small economy. Imagine, for example, that you have different escrow requirements or different collateral requirements to make certain types of transactions or loans. And so you would assume that that would affect behavior, right? And so what you want to be able to do is potentially modify those in different ways to make economics experiments possible. So in order to be able to experiment, right, we need to be able to have a baseline. So what we need to do is have some uniform mechanism to describe miniature economies that we can then change the rules of, or we can change the agents, or we can change the endowments. So we want to have a system that we can readily adapt to different scenarios that we're trying to experiment with. And so what we're going to say is we're going to adopt, as we mentioned earlier, the analysis of microeconomic systems provided by Vernon Smith. And so what we're going to say is that there are fundamental components to these economies, as Smith sort of talks about in his key works in this. And we're going to talk about them from the perspective of Smith's theory paper. And then as you go through these and focus more and more on mTree as a programming tool, you'll see how we can make use of these concepts programmatically. So one of the things when we start to describe these sort of small economies is we can look at a first component, which again we've kind of alluded to earlier, is that there are agents. So these are what we're going to call, we would appreciate these as individual decision makers in an economy. So they could be a buyer, a seller, or something else, someone that's making a decision. And generally speaking, we can assume that they have an aim to change their environment in some way, shape, or form in order to increase their own, value that they have. Right. So imagine someone's attempting to transact in a market. normally they'll want to do this because they're trying to increase, are they trying to maximize utility or something like that, right? Some type of value function that they're actually trying to optimize. At the same time that we have these agents, um, they have to have some access to resources they can trade for. Again, this could be currency, it could be underlying goods. And so, one of the ways you need to think about this is that the objects, the assets that the agents have access to or control over should be understood in some sense as a property right maintained by the environment. That is, they might have, you can't think of them as simply going around with a, change purse with coins. What we're saying is that there's these agents and this theoretical description of an economy, and then they have claims on assets or real goods that are described in an environment. And so what happens is there could be multiple agents sort of existing and attaching to a particular environment, and they have these property right claims on goods in the environment, and then they can exchange these rights in effect, right? So I can exchange for a good by giving you money, or vice versa. And again, it's a property rights exchange. And so one of the things we can also look at is the rules by which the agents actually transact. So there are institutions, that's the term that we'd like to use here, and these define the ways in which certain types of exchange can actually be conducted. So you might, again, going back to these transactions we were suggesting earlier, we might require collateral be posted prior to making some purchases, or affecting a loan or something along these lines. And so we can see at this point the three key terms we want to really emphasize are agents, environments, and institutions. So once we have described these individual components, we now have what we would call a microeconomic system, and these systems can support transactions. One of the things we have, though, in these microeconomic systems up to this point are three components. Again, agents, institutions, and environments, but we need to actually have them be able to communicate effectively to transact. So what we're going to say is that there's some type of message space, and so all of these components interact in some way with these messages, right? And there's a vocabulary of allowed messages that you would normally have, right? So for example, just as someone can't go into a store and just start, screaming randomly, there are certain messages that must be used in order to affect transactions. Again, at least in this theoretical environment. So what we'll note is that each of the individual components then must be capable of sending and receiving messages. So the agent must be able to send a message to the environment saying, environment, please shift the property right from myself to this other person for a currency or an asset. Similarly, if there's an auction, they must be able to bid, and these messages that contain their bid information would go to an institution, which would then accumulate all of the bids offered and then identify who's the winner. And so, again, the key idea is that messages is what make these components interact. The messages themselves can't be arbitrary. And so normally there'll be some mechanism where you specify the possible message space in the microeconomic system. And this is a key point to consider, which we'll emphasize later in the programming sections on mTree, in these mTree screencasts. So what'll happen is you'll need to actually specify the types of messages that any individual component can receive. And once you've specified those, you'll be able to identify that an agent, for example, might be capable of sending 5 messages and receiving 4 types of messages. So it's important to use that, especially when you want to identify certain behaviors that you might see in the experiments. Okay, so now what we're going to do here is we have a diagram of an economic system, and obviously it's fairly simplistic, but what you can see are sort of the basic connections inside of a microeconomic system. There's an environment, there's a single environment, but then you can have multiple agents, and you can potentially have multiple institutions. One thing to note, the direction of the arrows is only indicative of sort of where things belong. So the agents and institutions belong or attach to this particular environment, which might have something to do with, for example, a particular run of an economics experiment. That doesn't mean that that's the only way they can communicate or anything like that. It simply indicates that they're subordinate to the environment. Okay, so once we have a microeconomic system, what we will also potentially develop is what's called a microeconomic system sequence diagram. And a microeconomic system sequence diagram is intended to identify and describe the sequence of messages that might pass around between the components inside of a microeconomic system. So, what you'll notice in this is we have three columns: environment, institution, and agent. And then we have a number of rows underneath those three items, those three columns. And so what you'll see is if you follow the numbers, you'll see where the messages go. Now we'll talk in a second about the structure of the messages, but this is just simply showing you the order that messages might occur. So the environment might send a message to open the market to the institution. The institution in message 2 then asks the environment, please alert the agents that you're aware of that I am now open as a market. The environment then decides it will send a message to all of the agents it knows about that they should register with that particular institution. The agents, as seen in step 4, will then register against the institution. Imagine they're simply registering at an auction. And then once the institution's aware of all the agents that will be participating, it will then send them a note saying bidding is now open. And then each individual agent will be able to submit the bids, and the institution, depending upon the rules encoded inside of it, will eventually collect all of these bids and then award the winner. And so these types of diagrams are actually very helpful to become familiar with um, in order to diagnose problems that might be occurring inside of your economics experiment or MES, and also to plan out the sequence of steps in your MES, especially if you have multiple programmers working on these types of projects. You'll want to separate out the different component development potentially, and you'll want to just define it and say, I'll work on the environment, for example, you work on the institution. So the institution developer could say, I will accept messages for opening the market, for registration of agents, and for bid submission, right? And then they might say, I'll alert the environment that agents can now register, and so on and so forth. But if you think of it as a way of identifying the types of messages allowed, these types of diagrams can be incredibly helpful in both describing the function and the capabilities of the microeconomic system, but then also debugging any problems that might occur in development and experimentation. Okay, so now that we've described sort of the sequence diagram and how these messages flow, it can be useful to actually consider the messages themselves. So what we're going to do in mTree is allow you to define messages again in an arbitrary way as long as they're pointing to something on a component that will actually react to them. And so you can use whatever code you want. And this is similar to the underlying theoretical models developed by Vernon Smith. And so here what we simply say is that the message will contain a limited amount of information. It'll contain information about the sender, so who's sending the message, who's the intended recipient. It'll also have what we call a directive. And so directives are similar to, they sort of state what the expected handler for the messages on the receiving component. So, for example, the agent, when they're sending a bid into the institution, might have a directive name of bid, and the institution, when they receive that message with a directive of bid, will say, "Oh, now I need to look at the payload." Which could include, for example, the value that they're suggesting for their bid or something like that. And so those will be how you sort of develop these types of messages. And so you generally will have a limited number of directives you'll build in your entire MES, and you should be able to define it. And normally, the MES sequence diagrams are a useful graphical way to identify the different types of directives you'll need to program for. We'll cover this in greater detail in the mTree programming screencast as well. And so, again, with this, once you've defined these messages, the communication between each component will be done with these messages. And so, the only thing you'll normally have to develop is simply how do you process messages that each individual component receives based on their directives and payload. Okay, so at this point, we've talked mostly about theory, and so one of the things you might have, concerns you might have at this point, especially if you're new to programming, is that this looks complicated or it might look complicated. If you're a seasoned programmer and we've shown you these components, you might think this looks exceptionally complicated simply because the expectation would be that these systems are all operating in a concurrent fashion. That is, all of these actions are more or less running at the same time, and thus each individual component can send and receive messages at any time, so that you could have multiple components receiving or sending messages simultaneously. And those who have done any programming know that this ends up being a problem in concurrency and knows that generally speaking, this is very complicated. However, with the development of mTree, we've attempted to reduce as much of this complexity that you might anticipate as possible. And we argue that we've been somewhat successful, at least in doing that. And so, in particular, from a programming model, we only require the experimenters to focus on the sending and receiving of messages. Thus, you can develop an entire mTree microeconomic system, editing only perhaps 3 Python code files, and you only have to edit a certain amount. They will run by themselves, and we'll go over this in the both the programming and the running of experiments in future screencasts. So for each of the components, generally you'll write your code, right? So typically you'd at least have an agent, an institution, an environment, and so that would be the minimum amount of code you'd have to write. Would simply be to set that up. There's additional configurations, of course, to run the experiment. For example, how many agents to have, but that's typically configuration driven, and you can do that at a later time. So the idea here is, so what you should focus on first is, I only have to program the individual components here. So this is again why we suggest spending the time to think through the sequence diagrams and really just identify the types of sequence diagrams that your particular component would be involved in. So if you're focusing on an agent, you might only have to worry about, for example, submitting bids and then being alerted if you're the winner. Okay, so one of the questions, and again, in anticipation of things that developers might expect, what makes this programming style possible? Because normally when you're writing a program, you have to maintain a large number of files and all sorts of stuff. So how can we actually get it so that we can make it so that it's relatively simple to develop this type of computer code? And in particular, what we're actually making use of it's a technically old-fashioned way of uh, working on uh, concurrency and computing. And so there's something called the actor model. So if you peruse the entry at Wikipedia, you'll find out that this was a model developed in the early 1970s to handle particular types of computing workflows, and it's all done by message passing, right? And so if you look at the actor model and its initial descriptions in some of the early papers, you can find out that it provides a pretty straightforward way of looking at concurrent computation. The benefit being you only have to develop the individual actors, in this case, the components of an MES system, and then the framework that provides capabilities will handle the actual message passing between them. So you specify the message and where it goes, and some other code will actually ensure that it gets there. In particular, in the actor model, and you don't need to know too much. Perusing the Wikipedia entry should be sufficient for most purposes. The actors end up being the atomic unit of computing, so it's not a lot of complicated if statements or conditionals. It's just you need to have something that can handle, um, receiving messages in principle, right? And so with the actors as the atomic unit, they're capable of both receiving messages, changing their internal state, and sending messages. One of the things that's important to emphasize here is obviously you can see that there's references to both receiving messages and sending messages, but also changing state. One of the benefits of the actor model is that it effectively limits the state that you have to deal with. And what we mean by state here is the variables accessible by the individual components in the microeconomic system. So, for example, if the agent is concerned about their endowment, they're trying to recall how much money they still have left. You don't have to maintain a large database or a large table that says this is the endowment of every agent in the system. You can simply attach the state to the state of the agent, their endowment. So it could be that they have $5 or $10, and you can simply maintain it inside the individual component. Similarly, with an institution, you might say there are 5 bidders coming in or that will be submitting bids, and the institution can maintain that on its own. So this again affords the an ease of development, which might be difficult to see at first. But again, if you follow the suggested process of defining a sequence diagram, you can then simply work on your own component. And again, all you have to do is say, these are the types of messages I expect to receive. Then you can think of this is what I'll have to change. So for example, if it's bidding, you might have to maintain as an institution, right, that's running this auction, that all I need to do is identify what is the current high bid and who sent it. So imagine you've just been receiving bid messages, right? So the directive is bid, you know who sent it, and in the payload you know what they submitted. So anytime you, for example, see a bid higher than the previous high bid, you simply update the high bid, the internal state of the auction institution, and you also link it back to who sent it. So it's reasonably straightforward to do. Again, if you can write it out as a sequence diagram, that will prove to be very, very helpful, especially if you have multiple developers working on a microeconomic system. So again, the key thing with this, if you want to reflect and look at the Wikipedia entry for the actor model, is that you'll have this atomic unit of computing, which can receive messages, send messages, and change the state of the actor. And you also generally won't have to actually write any code to affect the sending and receiving of messages. You simply type in send and who you want to send a message to, and everything else happens for you. You don't have to think through how you're going to actually communicate with the other components in the MES. So that's a wonderful benefit of using this particular programming framework. So now that we've talked about these types of things, we'll very briefly touch on the basics of mTree and describe them. So mTree is simply a framework for writing the components of an economic system and then letting them communicate. The programming language used by mTree is Python. It allows you to develop agents and simulate economic transactions, and it also allows you to use um, various web interfaces to have human subjects interact with your experiment. The key feature here, the key separator, is that you can have the same code work both on the agent side for a simulation as for when you use a human subject to run an experiment. So that's a key differentiator between mTree and much, in fact, probably all of the other experimental economic software available, is the fact that you can reuse the same code. Uh, it also emphasizes the actor model, which allows us to use concurrency out of the box, whereas many other experimental economics frameworks would not allow that, certainly with human subjects. Or if you wanted to develop your own experimental framework, you would have to develop your own concurrency code, which could be fairly complicated. So mTree is designed to allow for the rapid construction of these microeconomic system components. And again, it does this by allowing researchers to simply write code to handle messages and not have to get involved in either the concurrency problems or any of the other kind of peculiarities of programming these types of systems. Okay, so at this point, you've got a very high level overview of microeconomic systems as they relate to Vernon Smith's earlier work. There'll be a link in the video below in the description to that paper. There'll be a link to the Wikipedia entry for the actor model, and there will also be a link to the GitHub repo. It won't be particularly useful in the first day, but once the Screencast 2 is available, we'll actually introduce mTree itself. We'll assume that you have Python installed and available, and then we'll walk through downloading and installing mTree, and then putting together an initial example experiment and running that. If you have any questions, please feel free to talk to your REU coordinator, and they will forward the questions on to